Nobody has questions? Or are we looking? Anyone looking for questions? Nobody's looking for questions. So nobody has any questions? Okay, fair enough. All right then. We're going to do a couple things today. First of all, we're going to work on some stuff in IMFs. So if you do not yet have your book, go get a book. Yes. You do have a question. Okay, let's go back to questions. There we go. Yes. Yeah. I thought the answer is like, but don't have signal. Okay, number 27. The answer is B. Which of the following diagrams is the most likely representation of the product of the reaction? Okay. So the answer is D. So, you know who can never have more than one bond? Never, ever, ever. H and F. So that means even though we don't like it, yes? Not this one, not this one. Not this one. Has to be this one. And even though boron is stable with 6 electrons, technically it can. So what we would have is we would have N, H, H, H. It's got a lone pair here. Boron technically has kind of an empty spot, although it's happy with 6. It can deal with 8. Like 8 is doable. And so what will happen is that nitrogen will share both of its electrons and sort of slot them in there. Yeah? But yeah, you can do that by elimination if nothing else. Yeah. Number 33. And Juno, you wanted 22? Okay, 33 and 22. Sorry? 23 and 22. Oh, well, then they're right next to each other. So let's go back there. 23 and 22. Okay, so 23, which best represents the bonding in N2O considering formal charges. All right, so we want to have the lowest number. Didn't we do this one last day, like in our notes? Didn't we? Okay, anyway, regardless, nitrogen, the assigned electrons is 5, or sorry, valence electrons. And 1, 5 valence electrons minus 6 assigned electrons is -1. Oxygen, 6 valence electrons minus 1, 2, 3, 4, 5, 6 assigned electrons is equal to 0. We want our negative charge to be on oxygen rather than on nitrogen. So let's see if we can do better for oxygen. And I feel like maybe this one. Let's try this one here. So nitrogen number 1, we have N, which is 5 electrons minus 5 electrons is 0. And the oxygen is 6 electrons minus 7 electrons is -1. Now, did I go through that process too quickly for anyone? Would anyone like me to break that down a little further? No, we're good? Okay. So this is a good, so this is -1, this is 0, this is -1, this is 0. We want to have our negative charge on the more electronegative atom, which is oxygen. So out of these two structures, it would be this one. I happen to remember from last day that these weren't as good. And you can just take a look at this and you can say, I've got oxygen has 1, 2, 3, 4, 5, 6. That's a normal oxygen, right? Nitrogen has 1, 2, 3, 4, 5, 6, 7. That's a -2. Oxygen here, that looks terrible. That's not even a good structure. We've got only 6 electrons on the oxygen, so that one's out altogether. Yes? Okay, so we're down to answer B. Is that good? Okay, cool. And then 22, we have C6H6. Do you guys remember the name of this compound? This is benzene. And it shows the 2 resonance structures. The phenomenon shown in the diagram best supports which of the following claims? All the bonds have the same length. True. Done. I don't even need to read any further. Because if I alternate, double, single, double, single, double, single, but then it's single, double, single, double, single, double, it averages out to 1.5 each, so they'll all be the same length. Is that good? Yeah? Okay. You don't even have to look at the rest of them. Anything else? Yes? Okay, so what the, I believe the quote from Teams was, what the flip is ionic character? So basically, which one is the most ionic? So we have a spectrum from the difference in electronegativity going from 0 up to 4. Okay, and we have a choice between, and so down here we would have nonpolar, covalent, and then in the middle we would have polar, covalent, and then we would have ionic. Now, something that is over here is more ionic, and something that's here is less ionic. Yes. The smaller the difference in electronegativity, the more nonpolar it would be, or the more covalent it would be. So more ionic character, I'm guessing it's going to be this one because calcium is so far away from chlorine. Let's just grab our periodic table for a second. We have copper and chlorine versus calcium and chlorine. Oh, they're even in the same row. So yeah, it's going to be calcium is going to be less electronegative than copper, so the difference will be greater. Yeah? Okay. Anything else? Okay. Nothing else? Yes. 10? Which of the following bonds is the most polar?
So like the most ionic kind of.
Well, okay, so we're in our 0 up to 4, and we've got nonpolar, and we've got polar, and we've got ionic. So now we're in this region here. Yes? Because these are all covalent bonds, so they're either going to be nonpolar covalent or polar covalent. And so you want the one that is, this would be the, like over here, in this region would be the most polar. So the difference in electronegativity would be the greatest, and over here would be the least polar. So you again would look at the difference in electronegativity. Remember, hydrogen and carbon are approximately the same. They're similar. Okay, they're very similar. Remember Fonch? And the C and the H are approximately equal. Yeah? So it won't be CH because that's pretty nonpolar. Out of our other ones, now we're going down the periodic table. And if we look on the periodic table, who is the most electronegative? We have carbon bonding with either chlorine or bromine or iodine. Who's going to be the most polar? Carbon with? Cl, chlorine, because chlorine is the most electronegative of those three. Yes?
So this why it goes to the.
Well, if you've got, paired with any metal, it'll become more ionic the more up here you go because you'll get the more electronegativity. Okay, so with our other one, we were pairing, you have to look at who you're pairing. So you'd say, okay, in the last one, I was pairing calcium or copper with chloride. So who's going to have the biggest difference? Right? Calcium's going to have the biggest difference in electronegativity. And in this one, we're looking at carbon. Pairing with either chlorine or bromine or iodine. And carbon is fairly nonpolar for a, because it's further left, it's fairly nonpolar for a, nonmetal. So chlorine is out of those three is the most electronegative. So it will have the largest difference in electronegativity. Yeah. Yes? I think so. Probably. Yeah. Anything else? Yes. Oxygen paired with those three? I would want a table of electronegativities. I don't think they're going to give you something like that because it's less obvious. Yeah? Okay, pairing those three with carbon says, oh, I'm pairing them with something relatively not electronegative, so I'm looking for something that is electronegative. Yeah? Yes? 16? Yes. Mm-hmm. Our lovely little graph. So we have our potential energy diagram, and we are looking at H2, N2, and O2. Okay, so we're trying to figure out which of these is H2, which one is O2, and which one is N2. So first of all, who's going to have we've got hydrogen is a teeny tiny little atom, yes? It's a single bond. We know that oxygen is much bigger than hydrogen. And what do you know about oxygen? What kind of bond is between the oxygen atoms? Double bond. And if you're like, why? Why is there a double bond? If you look at the oxygen atom, 1, 2, 3, 4, 5, 6, you have 2 unpaired electrons, so oxygen is going to double bond with the other oxygen. So you'll have 2 bonds for each oxygen. Is good? Yeah? And nitrogen, do you know how many bonds are in between nitrogen? 3. 1, 2, 3. And that's because nitrogen has 5 electrons, so you can form 1, 2, 3 bonds. So you're going to get 3 bonds on the one nitrogen and 3 bonds on the other nitrogen. It is worthwhile knowing that oxygen forms double bonds, nitrogen, like the diatomic atoms, nitrogen forms triple bonds and fluorine forms single bonds, just so you don't have to think about it very hard. So who is going to have who is the strongest bond out of these 3? Oh my dear God, everybody, who's the strongest bond? H, O, or N? N, thank you. What part of the graph tells us the strength of the bond? It's how far the dip goes down, okay? Okay, so this one's going to be N2 because we have a triple bond. And who's going to be the shortest bond? Hydrogen is going to be the shortest bond. And what tells us how short something is or how long it is? Bond length. And how do we measure bond length? We go from the origin, not the origin, we go from 0 out to the dip. Does that make sense? From 0 to the 0 to the dip, 0 to the dip, 0 to the dip. Yes? So 0 to the dip is our bond length. And so hydrogen is going to be this one, and that leaves oxygen is that one. And there we go. That should do it. Yes?
Can you tell me what is the correlation of the atom size in this potential indicator?
Well, I mean, if we were to compare hydrogen with fluorine, I feel like fluorine would probably be less strong than hydrogen because it's a bigger atom and so the electrons are further apart. But I could be wrong. Protons? I don't know. But it's more electronegative than hydrogen, so they're both pulling on those electrons really strongly. I don't know. Yeah. I don't think they're going to ask that. Okay. Yeah, usually. So you're looking at the number of bonds. If you were looking at fluorine and chlorine and bromine, just let's say.
Yeah.
So this would have the shortest. And because it's shortest and it's a single bond, it would be the strongest. Okay, Cl2 would be in the middle, and then Br2 would be the longest and the weakest. So I guess by the same logic, then hydrogen should be the hydrogen would probably be even shortest. 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 Okay, and the strongerest. Does that make sense? Yeah. Okay. Cool. Huh? 24? Yeah. I don't think so. No, we did 22 and 23. 24. Which of the following support the claim that NO3 has 3 resonance structures? It's non-polar. It is not polar. The nitrogen to oxygen bond is 90 degrees. That has nothing to do with resonance. That's just a stupid answer. One of the bonds is longer than the other two. That would not support resonance. Resonance makes everything equal. Yes. And one of them is shorter. No. So it should be A. Is the answer not A?
It is.
Okay. So if you look at it, I mean, you've got an N. You have an O, O, O. We have a 1 1/3 bond on each of these, yes? Is that polar or is that non-polar? That's non-polar because it's symmetrical, right? Everything has the reason.
If it is a polar species, what about the charge?
Well, polar means has a positive end and a negative end. Yeah? ¿Algo más? Anything else? No? Okay. I'm a little bit torn because we only have 3 days left. I have things to teach you, but I also feel like you could just do some review and learn in the process of doing some of the reviews. Is anyone finished all the reviews? Nobody. Okay. Would you like to work on some of the reviews today? Okay. I will point out just a couple of things that you should do along the way. You should make sure that you're okay with molecular polarity. I think most of you have a pretty good grasp on it. This is in Unit 12, 12.2. Oh, let's pick this one. If you have any questions, if you're like, I don't know whether that is polar, then you should probably watch this video. Okay, this is on page 28. If you look at this, and you can't tell me which of these things is non-polar or polar, then you should watch this. How about bent? Is bent polar or non-polar? Polar. How about trigonal planar? Non-polar. Tetrahedral? Non-polar. Trigonal pyramidal? Polar. Okay, anything that's asymmetrical is polar. Unless it's like, unless it's like, O, 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 right? Because O all has the same electronegativity. Okay? And the other thing, no. London dispersion forces. I did want to mention one thing in the London dispersion forces just before you go, and that would be on page... On page 75. Page 75. And that's in your duotang book. I think most of you know, I hope that most of you know, that there are two main factors that affect London dispersion forces, and you should know the first one. Polarizability. How many people are familiar with that term and feel like they know what it means? Polarizability. I got 2 people, 3, 4, 5, 6. Okay. If you don't know, polarizability means if we look at fluorine and iodine, who is more polarizable? Iodine. Why? Because it has more electrons. Okay? So polarizability depends on the number of electrons. They will often tell you the molar mass rather than the number of electrons. If you are told the molar mass, a higher molar mass corresponds to a larger number of electrons. They do not want you to say this is more polarizable because it has a higher molar mass. They want you to say it's more polarizable because it has more electrons. Okay? But they will give you the molar mass, because that's a quick way that people judge the polarizability, is just looking at the molar mass and going, oh, it has more electrons, it's more polarizable. The second one we haven't really talked about, and that is on page 77. We have neopentane, and its boiling point is 282.7. N-pentane, so these both are C5H12, C5H12, 309.4 Kelvin, boiling point. Who has stronger intermolecular forces? Neopentane or N-pentane? Which one? N, yes. What type of intermolecular forces? Are these polar or nonpolar molecules? These are nonpolar. If you have nonpolar molecules, what type of IMF are we looking at? LDFs. Now, we have the same number of electrons because they're the same structure. Yes? C5H12. Can you think why we might have better stickiness between those two on the right compared to the one on the left? Pardon me? Yeah, the shape, because what we've got here is we have all that surface, and here we have that. Yes? So which one is going to have stronger forces? I mean, you can just imagine it like Velcro. Okay, this one has, if you have a longer shape, wider shape, it's going to have stronger forces. Okay, so that is our other factor. If they are the same and they have a longer shape, then they will be stronger. Okay? And that's it for that. The shape of the molecule. Long, skinny molecules have stronger dispersion forces due to the increased surface area. Okay? So that's it for that. Ooh, and this one, which will have the greater effect? This is important. Dipole, dipole, or dispersion. If the two molecules are of comparable size and shape, or they have similar molar masses, if they have similar molar masses and shape, what can you say about their LDFs? LDFs will be the same.
So you measure LDFs, but actually it's higher.
Pardon me?
If it's the same, like how do you measure LDF? Is that higher or lower?
You can't really. You'd say they're about the same. Okay, so they're about the same. So who is going to determine the properties of a substance, its boiling point, its vapor pressure, all those things? Is it going to be LDFs or is it going to be dipole-dipole if they are of a comparable size and shape? It's going to be dipole-dipole because, and this is only for things that actually have a dipole. So if you were comparing, I don't know, C, O, H with C, let's just assume these have similar mass. What would be responsible for the higher boiling point of that one? The hydrogen bonding, okay? So if you see something with a dipole, or if we had C, O, C, This will be somewhat polar because the oxygen is polar, and in reality, this molecule goes up, down, and we would have an O right there. Yeah, so that would be a polar molecule. So this would have dipole. Yeah, so which would be the highest boiling point? It would be this one because it has hydrogen bonding. What would about this one? It would be the second highest because it has dipole, and this one would be lowest because all it's got are LDFs. And that's because they're all similar size, shape, and mass, okay, number of electrons. What though if we have one molecule that is much larger than another? So let's say I had C, O, H, ba-doop, 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 boop. And I had C, okay, and what if I told you that this had the higher boiling point? What accounts for that? Not many more CC bonds.
Oh.
Stronger what? LDFs. Yeah, stronger LDFs due to having more electrons, due to being long and skinny, right? The LDFs are going to be large. So even though we have H bonding here, right, we can have you know, another hydrogen here and then our O and then blah, 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 blah. Even though this can H bond, you can have something that is nonpolar with a stronger force in between if it's got sufficiently high LDFs. Yeah? Okay, and I think that's it for that. Yes. Okay, that's all I wanted to say. Do you want to work on review? Yes.
The number of bonds doesn't change that well.
The number of bonds? No, it's the number of electrons in the shape. Yeah. Yeah. I mean, the number of bonds contributes to the overall size of the molecule, so yeah.
Hybridization.
Pardon me? Well, okay, so here's the deal. That is the background theory behind SP, SP2, SP3. You are never going to have to explain it. You're probably only ever going to have to say, what is the hybridization of this atom? Can you do that? Yes. So we don't need to do that, and we ran out of time. So there we are. I'm kind of sad because I had a conda llama, or I had a llama conda in there, but you know, it's a hybrid between a llama and an anaconda. And by the way, if I don't see all of you working extremely, extremely hard, I have things to teach you. So I would be thrilled to just talk about molecular solids, covalent solids. They will be on your test. I will go over them tomorrow. Yes. Yeah, okay, so if you like imagine that you have a spring, yes, and the spring has its natural, you have to start with far apart without something, right? And it might feel like point, right? Especially if it's but eventually it's going to stabilize out of that state. And you can't, it won't stay here. This is a high right? Yeah, and then go back to the steady state. So this is what we call equilibrium. It will actually, have this kind of vibrations. So it does get bigger and smaller, but it averages out. Well, the closer it gets, I mean, it's you cannot get to the point where you want to do it. So they have to get the meters. It's like my house in space, right? So they can get this close. Yeah. But having to do that, they can't. Yeah, it's like. Yeah. So that's like pushing them as close as you possibly can. And they just, I mean, naturally they will want to go back to their level. Yeah, they're like here, right? That's all kind of vibration. Only if you had two atoms that were coming together very, very closely, right? And there was enough momentum that snapped. Right? And then they feel like, wow! Yeah, it would never stay up. Yeah.
Oh, B, A, L. B, 4. Okay, L. Yep.
I didn't have zero.
Yeah.
Wait, so B is six.
Yeah.
Is around.
Yeah.
AL is six.
Yes.
Just like AL six.
Yep. And if you look at the, right? Yeah. Around this way. Yeah. Wait, Mom, sorry. Yeah, no, it's like.
Well, honestly, plus three is. I guess this is.
No, when they do the north of although, yeah, it's yeah. Yeah, because if it's smaller. Smaller. Yeah, but if we have if you install some of these in the alloy, it will increase you're simply like adding in for.
Yeah, literally, because.
But if you replace a pure iron, pure lithium, yeah, mix other things. But you got sodium. Yes, they all have. So it would be the stronger part of sodium, which is already I'm sorry, that's not. Oh, yeah, and then so yes, because F and C are similar in size, so they won't, affect because these are lost. Okay. This is the only one that actually does. Oh, wait, one where you have two electrons. species so that it's like it was six, but in this was yours. Yes. Oh, yeah. That one just doesn't have any weight. I don't know.
No.
No. So, well, it can be like a spirit of service. Yeah, I think C, yes, this is great. But, if you have. Because this one is. Wait, you're right. I don't know if this. Yeah, exactly. So this is the service layer. This stage is like this. But you guys
Not.
you should not have this full of this. And it's like it's sort of animated, but it's all just it's like
All the way to the nerve.
CRs are the same size as iron. And it's like
All the way I can that's the C.
yeah.
All nerve.
Yeah. Yeah, that's yeah. Yeah, that's what's so I so what are you doing on your phone? You're supposed to be working. Not to be like, yeah, it's not fun. Science. Oh, so for I-Week, we have something on the calendar. I'll start teaching gases, but you're welcome to come or not. Do you know what I mean? I'll record it.
When is it?
When is it? It's 10, I think it's at 10:30 on Thursday. Okay, so I'll start teaching gases. But if you're like, I have an exam that day, you know, because I know a lot of you are in grade 10, just skip it, okay? It's either I have to do that or I have to go help out with the grade 8s, right? So I'm like, no, I will schedule a tutorial for my 11 enriched students. So even if it's just me in this room teaching to myself, that will be okay. I know there's a couple of people who definitely do want to come in. So if you do come, you won't be alone, but feel no huge obligation. I put it at 10:30, so it was before, you know, the afternoon, but not too late, not too early, okay? Yeah. Wow. Yeah. Oh, I just said next week during my week we have a tutorial scheduled on Thursday at 10:30. I'll start on gases. Okay, but if you are not here, as long as I don't. No. Yeah.
That's not ionic.
Yes. Why does it have a higher? So it has. Well, it's number one, anytime you have a market, it's not like in a life.
So it's like you get a graph, it's like how you get solution like that. That's like a person.
Yeah.
Like honestly,
And so this will be. Yeah, so that's what I did. I did. Yeah.
It doesn't say that's why some of the Russian it's always.
So you like you guys
We're not doing. Wait, we're on the middle.
What are the?
Why is it always left the other side of the
So like some.
Say,
Isn't there like? So there's. I know I read it.
I'm gonna put my on. Yeah, she had. I think you know very well.
It's. I didn't.
Yeah.
I've had questions about, from a few people, about valence bond theory and hybridization, because we skipped it. That is the theory behind why hybridization is sp, sp2, and sp3. You're not going to be tested on the theory. What's going to happen is we're going to point at a carbon or an oxygen and say, what's the hybridization? And you need to be able to say whether it's sp, sp2, or sp3. You don't need to be able to explain the wheres and whys of it. If you're interested, talk to me later, okay?
This one, yes. It's like one so that's like yeah. I'm not sure about that. I think you said I don't really. No, it's also not actually so that work like it's 2 and 1 with 1. Then we also just would be like more or 8 like that. Small. Then small. Right? Yeah. If it's too oxygens, then we also yes, but yes. I don't think that there was. Okay, so we have small like don't worry about chromatography. We're not going to get to it. We'll have to cover it later. Okay.
Does anyone want the thing I printed out on IMF's polarity properties of solids and liquids?
What is that?
It's what I'm going to teach tomorrow, kind of ish. It's my desperate attempt to like throw information at you, is what it is, because we only have 2 days left. It's here. You can grab one. You can grab it tomorrow if you prefer. But if you're like, I want to read about it before we do it. Yeah, so if you got a little extra time to do some reading tonight, you can read ahead.
Are they the same or different?
They're the same.
Okay.
Yes.
What is the hierarchical
Oh.
What is the hierarchical lithium?
Vapor pressure. So vapor pressure is two. No. No, did I not put it in here? Am I a fool? I'm a fool. That's okay. That's okay. It's okay. Okay, never mind. Okay, so how to say it? Okay, so this is covered.
Yeah.
This is a liquid.
Yeah.
Okay. Just naturally, some of it's going to evaporate.
Okay.
Yes? And what will happen is the moment you put the lid on, a certain amount is going to evaporate until this comes to an equilibrium where every time another one evaporates, then we need to have it go back down.
Yeah.
Yes?
Okay.
So the more particles that can be up in gas state, the higher the vapor pressure.
Okay.
Okay?
Okay.
So if you have stronger IMFs,
I'll be lower.
you'll have a lower vapor pressure.
Okay.
Yeah?
Sounds good. Thank you.
It's technically contemporary to You will be older. Like the other questions. The ones where it's like. Yeah. You don't flex it. That's not a basic. It's based on the larger Because like you're like saying, usually what'll happen is it'll be like, it's polar, right? They'll put like something like chlorine, polar. Here's all just get it on. Oh yeah, because CL, you know, that's why it's less dense. I would guess.
Yes.
That's okay.
Nice hot bottom.
Yep, I will walk in.
Awesome.
This is. Yeah, this is. Yeah. So this one. Because like, yeah, they're the same version, which is not for this case.
It was all the way.
CL, so you want something that's, so CL stays the same, or no, CL ages, because it just gets, yeah, and T gets smaller, so. And also could.
So it's
You
delta.
want to be saying, breaking bonds is hard, it needs a lot of energy to break bonds.
So that's what does it.
That is. Yes. Were you breaking? Also
Yeah, yeah. All right.
Yeah.
Yeah. Oh my god, so stupid.
Oh, yeah, no, that's fine, that's fine, yeah. Yes.
Yeah, yeah, I did.
Because isn't it? Or hang on. Like a filtering. Well, yeah, that is. I'll make it on the same one. So this is as far as how do you do that part? I did just a lot of that because I